So what I want to show you in this little recording is how to use Scifinder and some of the other websites to acquire data on the materials that you're interested in this case trimyristin. So we're going to start by opening a web browser, and I'm going to use Firefox here. And if I open Firefox, it should automatically open to the Blackboard page. And I'm going to go ahead and log into Blackboard using my account. Go to courses and courses I teach. So I'm going to the Organic Chemistry Lab, and under web links you'll see that there's a AIST spectral database, Sigma Aldrich Online, and Acros Online, and there's this Scifinder login. These are all databases. These are the two companies we buy most of our chemicals from, Acros and Sigma Aldrich. AIST comes from the Japanese scientific organization that has a lot of IR, UV, NMR, and mass spec data on a whole bunch of different compounds. And then Scifinder will search a whole bunch of journals, but it also has things like the CAS registry number. So if we were to click on the Sigma or Aldrich Online link, that'll open a Sigma Aldrich page. It would like you to register, but you don't really need to. You can use it without doing that. So we can immediately go in here and we can search for kind of anything we want. We can search for structure, we can do product name, CAS number. So we could type trimyristin, and we've got it in 3 different places. Glyceryl trimyristate is another name for trimyristin, so we could click on either of those. And here we have trimyristin from the European Pharmacopoeia Reference Standard. That's probably not what I want. And here's glyceryl trimyristate, which is greater than 99%. And it has a CAS number here of 555-45-3. So we're going to go ahead and click this glyceryl trimyristate T5141, and that will tell us that it's available in 1 gram and 5 gram sizes, and kind of expensive, $284 for 5 grams, $75 for 1 gram. So obviously we're not buying it. And here's the structure, right? It's got 3 14 carbon chains. So you've got 1 carbon here, and then a second to CH2, 11 more, so 12 total CH2 groups and a CH3. So a 14 carbon chain, C double bond O and O. Here you've got a 3 carbon unit. This is the glycerol part. Glycerol is 1,2,3 propane-thiol, and it's the trimyristate ester of glycerol. Another name is 1,2,3-tritetradecanonyl glycerol. Right? So trimyristin is a common name. Glyceryl trimyristate, also a common name. 1,2,3-tritetradecanonyl glycerol is the IUPAC name. So we can see its molecular weight, 723.16. We can get the CAS number, 555-45-3. Those are things to write down in the lab notebook. And then if we scroll down, it will give us the fact that this assay is at greater than or equal to 99%, so it's a relatively pure material. They're getting it from palm. We're getting it from nutmeg. It's the major triglyceride of nutmeg. It is not the major triglyceride of palm oil. That's tripalmitate. Makes sense, right? Palmitate comes from palm oil. And it'll tell us the melting point is 55 to 57 degrees C. That's from a literature source. So we could look and see what their literature source was, and we can show some more properties. It's got all kinds of things that here make no sense. So you could write that down, 55 to 57 degrees C. That's a literature source which you got from the Sigma Aldrich website. So we write www.sigmaaldrich.com. All this stuff here that's in a lighter gray, it's not necessary to write that down. And then we would say that the title of the page was glyceryl trimyristate, and the date of access is right now July 23rd. So we do our web reference correctly. Right. There are some articles down here. There are peer-reviewed papers. There's all kinds of stuff that might be relevant. Right. So Myristica fragrans, seeds, but what we're really after is the melting point, and it would be nice if we could get an infrared spectrum, but apparently there is no infrared spectrum here. So we can click on this protocols and articles, right? That's probably going to tell us what their literature source is. Here's the peer-reviewed papers, right? There are all 27 of those. Safety and documentation. That'll give us the fact that it's really not very, eye shields, gloves, type N95, respirator. I guess if you were going to be breathing in the dust, you might need that. But really, it's a relatively safe substance. So we can't get a infrared spectrum of trimyristin from the sigma aldrich. Sometimes you can, sometimes you can't. Right, you could click on myristic acid if you wanted to and kind of look up myristic acid. Right, there's the CAS number. And if you scroll down, again, it doesn't look like there's an infrared spectrum available for this. Sigma Aldrich Online has some IR spectra, but for a lot of compounds it doesn't. So we can certainly get a melting point from the Sigma Aldrich website, 56 to 57 degrees C. We can look at Acros Online, and again it would like you to register, like you to select your country. I mean, it really doesn't matter. We can claim we're from Australia. And now that we actually know the CAS registry number, we can type that in directly, 555-45-3, and that'll get us there faster. And so we have trimyristin, aka glycerol trimyristate. There's your CAS registry number, there's your molecular weight, here's your structure, right, showing the 3-carbon chain of glycerol, and then the long chain hydrocarbon. This one's showing it all the way out. You'll see that this one doesn't actually have an infrared spectrum available, and its melting point is listed as 54 to 58 degrees, which is a very broad range. That's a greater than 4 degree range, which means this is probably not a particularly pure sample. And if we look at the top here, we can say that this trimyristin is only 90% pure. So what we see is a depressed range, lower, starting at 54 degrees instead of 56 degrees, and a 4 degree C range instead of a 1 degree C range. So this is not a good literature melting point, because you don't really want a melting point of only a 90% pure sample. But what we can get from the Acros Online that we couldn't get from Sigma Aldrich is the infrared spectrum. So we can click on infrared spectrum here, and here's the actual spectrum. Okay. That's useful if what you want to do is just look, I did not mean to do that. That's useful if what you want to do is look at your spectrum to compare it, but it's not really giving us the numbers. We would have to estimate, right? There's 1,000, that's 1,516. So this is somewhere around 17, a little bit higher, between 17 and 1750. We'd like to actually have numerical values for that. So you could print this, you could right-click this, and you could take a screenshot, drag it over here and say, we'd like to download that and print that, so you could upload that to the website. I'm going to download that, and that'll go into my downloads. Here's my screenshot as a PNG file, which I can then open, and it'll automatically open in preview, and then you could upload that. So we have the spectrum, which is going to be useful for comparing it, but we really like to have some numerical values for these rather than just the numbers. The scale here on the vertical axis is percent transmittance. So 100% transmittance up here would be none of the light is being absorbed, and then down here the peaks go down, telling us that a lot of the light energy is being absorbed here. So we've got the region in here. This I happen to know is the carbon-hydrogen stretching region. This is where the carbon-oxygen double bond stretches. This is where the carbon-oxygen single bond of the ester stretches. And then these other groups here and here have to do with the fact that it's a long-chain hydrocarbon. So that's not exactly what we're looking for in the infrared spectrum. It's somewhat useful, but it's not going to tell us the numerical values. We can go to the AIST spectral database. and it will tell us where it's coming from. This is the Spectral Database for Organic Compounds, SDBS, from the National Institute of Advanced Industrial Science and Technology. That's where the AIST part comes from. The IR part is kind of edited by S. Matsuyama, S. Kinagusa, Gasa, K. Tanabe, and T. Tamura. You have to agree to this disclaimer, basically saying that you know it might not be accurate. And it tells you here that when you use the data from here in your publication or presentation, they want you to acknowledge it like this: SDBS web. Here's the secure HTTP, SDBS DB AIST Go Japan, this National Institute of Advanced Industrial Science and Technology, and the date that you access it. And I would add that you also want to give kind of the heading of the page, which is the compound. So we're going to agree to that disclaimer and use the data site. If you forget how they want you to cite the site, you can also go to these frequently asked questions, the FAQ at the top, and one of the things that you can look at is how should I make citations for SDBS, and it will give you that same information. Please put a reference in your bibliography, just like this, right? So it'll tell you exactly how to reference it. So we know the CAS registry number, 555-45-3. We can type that in directly and we can search. And it will come out with the compound. It's number 7886, propane 1,2,3 trimyristate, yet another name for this compound. So I can click on that. And then over here is all the different data that's available for it. So here's the structure, right? A C double bond O, 12 CH2 groups and a CH3. Here are the synonyms: trimyristin, glycerol trimyristate, glycerol trimyristate, propane 1,2,3 trimyristate. CAS registry number, molecular formula, molecular weight. And then over here, there's IR spectrum, both as a Nugel mol and as a KBR disk, proton NMR at 90 megahertz, and carbon NMR, which would be at 1/4 of 90 megahertz, because the carbon spectrum is always taken at 1/4 of the frequency of the proton. Since in the lab we're going to be measuring the IR as a KBR disk, we would like to use the KBR disk for our comparison. So here it is. This is a little bit of water, a little OH stretch. That hump wasn't there in the acro spectrum because they had a slightly more pure sample. And here we have our kind of hydrocarbon CH stretching region, our carbon-oxygen double bond stretch. And you'll notice that it's actually split out a little bit so that there look like there might be really two peaks in there, which makes sense because we've got two slightly different carbon oxygens. This one attached to the middle carbon, this one attached to the end. This is a CH2 scissor. There's a CH3 rocking absorption here. We've got our carbon-oxygen stretch here. We would expect actually to see two carbon-oxygen stretches because we've got a sp3 hybridized carbon-oxygen and an sp2 hybridized carbon-oxygen, and they probably show up at slightly different frequencies. We would expect the sp2 carbon-oxygen stretch to be a slightly shorter, stronger bond. So we see a carbon-oxygen stretch here. That's probably the sp3 CO, and then here is probably the sp2 CO. You'll notice the carbon-oxygen stretches are a little bit broader than, say, the CH2 scissor or the carbon-hydrogen stretching. That's fairly typical of carbon-oxygen bond. This is giving us what we didn't get from the acro site. It's giving us a list of peaks at 2954, right? That's got a transmittance of 43, right? That's this peak here. At 2917, that's a very strong peak, percent transmittance only 4. 2872, 56, right? That's this little peak here. 2860 at 13, that's this peak here. So we've got 4 different carbon-hydrogen stretches, and we'll be seeing a little later when we talk about how to process your IR spectrum, how those can be individually attributed to a specific CH stretch, right? We've got a peak at 1737 here, right? And a peak at 1729 at 16 and 26 respectively. That's my 2 carbon-oxygen double bond stretches from an ester. Around 1730 to 1735 is typical for an ester. Here's our 1471, that's our CH2 scissor, right? And we got some other peaks that are really small. Significantly, we've got this peak at about 1384, right? 77, and then 1375, 79. That 1375 peak, 1384, or 1392 is probably the larger of the two. that is our CH3 rocking absorption. There are only 3 CH3 groups, and there are a large number, right? There are 36 CH2 groups plus these two, 38 CH2 groups. We would expect the CH2 scissor to be stronger than the CH3 rock. And then we're looking here, right, at 1181, we've got something that's like 38. That's probably this peak here, right? That's the carbon-oxygen single bond stretch. And then we go down here further, we're looking at, 1095, 1113 is 68. This one here looks like it's probably this 1095 peak. So that'll be our carbon-oxygen single bond stretch from the sp3. And then this peak here at 717 with a 72% transmittance, right? At 72% transmittance there. That is a CH2 rocking absorption when you have 4 or more CH2s in a chain. And we'll talk about that more later. So we want to print this. So we can save this image, we can view this image, right? We can view just that frame. I'm going to print that frame, right, to a PDF file, and we can print that, save as PDF, call it trimyristin, tell it where we want to put it. I'm just going to go ahead and put it on my desktop, and I can save that. And then when I open that, it will automatically open in preview, and that gives me the website here. That's not exactly how they want you to cite it though, and it gives me the spectrum and then the list of peaks and the structure. So we can upload that as part of our upload. We can combine that with the Acros spectrum. Right. You can also print the entire page if you want, but if you want to print just the spectrum, then you want to right click and you want to go to print frame. Right. This frame, print frame. So those are simple kind of databases. Certainly it's good for getting pricing information from Acros and Sigma Aldrich. It'll give you purity. And from the AIST, there's a lot of spectral data. If we really want high quality data, then what we want to use is Scifinder. So you will have gone to Scifinder registration and created your username and password with your OO account. I'm going to go to Scifinder login. Because I'm using this at a Ohio Wesleyan email address. And I'm not going to save that password. And so now I'm into Scifinder. Scifinder is very useful. There's more than 2,000 journals in here. We can search for all kinds of things in Scifinder. We can search by research topic, by author. So if you wanted to find out everything that Dr. Pissner had published, for example, you could go in author name and you could type in Pissner. And then it's Alan, so you could put in A. Pissner. And here's Alan J. Pissner, that's probably him. Pissner A might be him, but there is zero reference for that anyway, so probably this Alan J. Pissner with 28 papers, that's probably him. Andrew R. Alexander, right? And we can get his references. So obviously he's done a lot of work with complexes of metals, electrochemical spectroscopic and O2 sensitization characteristics of synthetically tetrapyrrole complexes of palladium and platinum. That's almost certainly him, inorganic chemistry. That's where he would be publishing. And this Joel Rosenthal here, you can see, is the kind of lead author on a lot of those papers. Here's Joel Rosenthal again. And if we wanted to click on any of these papers, like we could click on this inorganic chemistry paper. And this is definitely a paper from Dr. Pissner. We probably have full text access to inorganic chemistry because it's an American Chemical Society journal. But before we can click on this link to other sources, right, it's going to say Firefox prevented this type from opening a pop-up window. I'm going to actually have to go to the system preferences and tell it it's okay. So I'm going to go to Firefox preferences, and under privacy and security, I can actually find the place where it asks if pop-ups are okay. So the default is to block pop-up windows, but I'm going to put an exception in here, and I'm going to type that scifinder.cas.org is an acceptable place to get pop-up windows. So now HTTP and HTTPS at scifinder.cas.org, it will allow those now. And when I click on link to other sources, it'll actually open up a window here that says it's directing me to the full text access. Here it is. All right, so there's the author information. This is coming from the University of Delaware, which is where Dr. Pissner did his postdoc with Joel Rosenthal. So if you wanted to read up of what he did in his postdoc, there's the paper, PDF full text. We could click on that. And there's the full text paper, which you could then print. If you're curious as to what Dr. Pissner was doing at the University of Delaware, there you go. And you can look up any of your faculty from your other classes and find out what their research interests are. But what I want is I want to explore a compound, a substance identifier. And I can type in my 555-45-3, the chemical abstracts service number for trimyristin, and search. And it's going to give me this compound. Here it is, tetradecanoic acid, 1,1', 1', 1,2,3 propane triaryl ester, yet another name for it. So if I click on that, here's the compound. Here are all the synonyms, lots of synonyms. You can buy it as dinasan 114 or esteride GM. Glyceryl trimyristate is there, trimyristin is there. Here's the melting point, the experimental 56.5 degrees C. That is not a very good melting point, because melting points should always be described as a range. Boiling point, experimental, 311 degrees C, so pretty high boiling. Here's a density. Predicted though, that's not an actual experimental data. And if we scroll down here, we got experimental properties. Right. Here's the thermal data. That's where you can find boiling point and melting point information. So there's a whole bunch of different possible melting points you could report. 67 to 68, 68, that seems out of line. That's probably not real. Most of our melting points seem to be in this 55 through 57-ish range. Here's one that says 55 to 56 degrees C. That's pretty good. That's close to what we saw at our Sigma Aldrich website. Right, 56 to 56.5. Again, that's close. That's reference 14. So that one comes from Russian journal, Akadnog SSSR. That's Russian. But reference 8, this one here is Chemical and Pharmaceutical Bulletin. That comes from Japan. That one we probably could get full text access to if we wanted to reference the 55 to 56 degrees C as a reasonable melting range. So I'm going to go ahead and click on that. 3 new lignans from the nutmeg of Myristica cagayensis. So that's actually kind of interesting, because it's probably coming from, they're isolating trimyristin from the same material, trimyristin isolated from nutmeg. This might actually even tell us what percentage the trimyristin came. And we can link to other sources and see if we actually have full text access to this journal. And if we don't, we can always interlibrary loan it. So it looks like there's an open access version. Maybe we can get that here. Not available online directly. Sometimes it is available online. It's just it takes you a little longer to get there. So there it is. There's an open access version. ChemPharmBull, that's the abbreviation for the Chemical and Pharmaceutical Bulletin. Issue or volume number 37, issue number 9 from 1989. Pages 2310 to 2312. And here it is, compound number 1, that's trimyristin. And it's giving us some, this is NMR data, proton NMR data. And we could actually print that paper if we wanted to. Here's the experimental data. It says trimyristin, melting point 55 to 56 degrees C. This would be a really good reference for the melting point, because it's from an actual journal. It's giving IR data, 1735, 1413, 1300. Doesn't give all the peaks. You notice it's not giving the 2900 range, because diagnostic peaks are the ones that are in here. Here's our C double bond O stretch, our CH2 scissor. We've got our 1255 and 1190. Those are our CO single bond stretches, and our 720, that's our multiple CH2 in a row rocking motion. And it's got NMR data too if you wanted NMR data. And you could read through the paper, and it might actually, if you read through it closely, it might tell you what percentage of the material was found to be trimyristin. But I'll let you do that on your own. So useful way to get to papers, if I go back here. And then also there's experimental spectra. So I could click on experimental spectra, and there's proton NMR, but there's also here IR. And we can see that there's IR spectral data. Here's the AAST data site. That's the same data site we got through directly by going there. Here's that paper that we just had open, right, where we found our paper, our reference. There's the BioRad infrared spectral data. I can see the spectrum there. I can click on it, and then this is kind of like the acros.com. It gives me a spectrum that I can compare, but it doesn't actually give me the numerical values. And if I click on the AAST spectrum here, it also doesn't include the numerical values. So you want to go to the AAST site directly rather than going through the Scifinder to get to the AAST. Here's another one from Chinese Pharmaceutical Journal. That journal is likely to be in Chinese, probably. We could click on it and see. I don't know, language is in English, so it's possible we also have full text access to that one. We can click on it. And in this case, probably not, right? We'd have to not available online. We'd have to request that by interlibrary loan if we really wanted it. And it's probably not worth that. So Scifinder allows you to plug in a substance identifier. If I didn't know the CAS number, I could have typed in trimyristin, and it would have taken me to the same place. And I've got experimental properties, I've got spectra, I can click on spectra, and that would have taken me directly to the section where the experimental spectra is available. Proton NMR, carbon NMR is even known, Raman spectroscopy, that's a different type of spectroscopy you'll learn about in instrumental analysis. There's a mass spectrum available, pretty much all of it's available from that Chinese Pharmaceutical Journal, which we could interlibrary loan if we wanted it. If you wanted to explore just an individual journal here, we could type in the journal name. Right? So if I knew that I wanted something from Journal of Organic Chemistry, and I wanted the most recent one, so the 2020 publication year, I could kind of look at the whole table of contents. It wants you to put in an author last name, and since I didn't, it's not giving me anything, right? So I could type in, I don't know. Well, I don't actually know anyone who's published in the Journal of Organic Chemistry, so I can't really do that. But if you actually had the journal, you could type in the author last name. Let's type in Brown. Let's see if Brown has published anything. No, apparently not. So I don't have enough information to use that. You can also type in research topic. So if you wanted to research, for example, the shelf life of tortillas, you could type in shelf life of tortillas, and there's 10 references that directly contain shelf life of tortillas as entered, 46 that contain both of those concepts closely associated. And you could find that there's a whole bunch of patents. Milled cereal byproduct is an additive for flour and dough. Nutraceutical rich carrot powder ingredient is incorporation into mixture immortalized corn flour tortillas. There's all kinds of stuff in the Journal of Functional Foods. Patents are not usually very useful, so one of the things I can often do is by refining, I can go by document type and tell it I really don't want patents, I just want journals. And that'll get rid of half of those references. So now I've got microbiological characteristics and shelf life of corn tortillas with and without antimicrobial agents in the Journal of Food Protection, changes in textural pasting and thermal properties of wheat buns and tortillas during storage in the Journal of Cereal Science. You probably didn't even know these journals existed, but there's obviously money in having a good shelf life on tortillas. And here's one that's in Spanish from Archivos Latinoamericanos de Nutrición. producing packaged tortillas with a longer shelf life, which have the qualities of fresh tortillas, effective preservatives and texture conditioners. Right? You can research just about anything by typing a research topic. And you can use Scifinder not just in chemistry, but also in biology, because there are an awful lot of biological journals. If you wanted to talk about apoptosis, programmed cell death in bacteria, you could type in apoptosis in bacteria, and there are 82 references on apoptosis in bacteria in a wide variety of journals that would help you to investigate that. And then finally, if you want to explore things and you don't know the name of the structure, but you know what it looks like, you can actually enter a given structure. So if I wanted to find out about methyl tert butyl ether, for example, I could draw the molecule. There's a tert butyl group, and then an oxygen, and then a CH3, and I could actually use my shortcut here to tell it that I want it to be a CH3 group by choosing the methyl group, and do an exact search. And I want the exact structure, and I want it a single component that's commercially available, and I could search for methyl tert butyl ether, and here it is, 2-methoxy-2-methylpropane. Right. Here's one with deuteriums on it, here's one with a carbon-13 label. I don't want those. This is the one I'd want. So there it is, ether tert butyl methyl, 2-methoxy-2-methylpropane, 2-methyl-2-methoxypropane. Apparently Driveron, MTB, methyl 1,1-dimethyl ether, methyl tert butyl ether, lots and lots of different names. So here's the boiling point, 55.2 degrees C. I can look that up under experimental properties and hit thermal. Right. And you can see there are a lot of sources that tell me that it boils somewhere around that 55 degrees C, 54 to 55, at 760 torr. Some of these are probably at reduced pressures. Its melting point is minus 109.6 degrees. And there's spectral data for that as well. If I wanted to know what its IR looked like, right, there's the IR in the AIST, that's Wiley Subscription Services, Biorad, lots of different places. Right. The CAS number for that is 1634-04-4 for our MTBE solvent. So structure searches can also be useful in Scifinder. That should give you an overview, and you can just play with Scifinder. I'm going to sign out now and end this recording. Sign out of there. And I'm going to close Blackboard and close Firefox. Yeah.